Okay, yeah, that's a good idea. Okay, thank you everyone for coming today. It is a privilege and an honor to welcome you all here to the Adriaan van Ballegooijen, am I saying that correctly, lecture. Today we have the privilege of a gathering for the first annual lecture in honor of Dr. Adriaan van Ballegooijen. And he was a visionary solar physicist whose remarkable career and contributions have left an indelible mark on our understanding of the sun's magnetic phenomena. Adriaan's journey began in the Netherlands, where his fascination with astronomy and mathematics led him to the University of Utrecht, where he developed his expertise in theoretical astrophysics, earning his PhD in 1982. His dedication to advancing science took him across continents here to the CFA, and he spent 25 years here. His dedication, he blended theoretical knowledge with cutting-edge observations to push the boundaries of solar physics, and his groundbreaking research reshaped our understanding of the role of magnetic fields in the solar corona, filaments, prominences, and the dynamic processes there. His innovative approach to modelling these complex magnetic structures set a new standard in the field, and that enabled scientists around the world to see solar activity in a whole new light. And through his development of a novel modelling toolkit and his commitment to sharing his expertise, he developed a spirit of collaboration and mentorship, guiding countless young scientists as they embarked on their own careers. And I think that really embodies what we do here at the CFA really well. So it's just wonderful to be able to celebrate his career. Even in retirement, his passion for discovery and his dedication to the solar physics community never wavered as he continued to inspire, support, and engage with researchers worldwide. I'd like to acknowledge the members of his family who are here today. Thank you so much for coming. It's wonderful to meet you all. And we have Christine Lackey, Aad's wife, Sarah Henry, his daughter, his sister, Hanneke, and her husband, Paul, as well as his sister-in-law, Linda. So thank you, everyone, for joining. As we inaugurate this annual lecture in Aad's honour, we celebrate not only his individual achievements, but also his profound impact on the scientific community. His work on the UVCS ultraviolet spectrometer for the SOHO satellite was a testament to his calm problem-solving and scientific rigour, which played a crucial role in the mission's success. Beyond his scientific research, his true legacy lied in his approach to building a supportive, collaborative environment within the solar physics community. He was a mentor who valued personal connections and was always willing to offer guidance and support those finding their way. I hope this lecture is going to serve as a reminder of his example, his empathy, dedication and commitment to nurturing the next generation of scientists. And in carrying forward in his spirit of collaboration and care, we continue to honour Dr. Adriaan van Ballegooijen. I'm so bad at saying it, I'm so sorry. My Australian accent doesn't help. His enduring legacy. But thank you so much to the family for your support and commitment, and absolutely delighted to welcome our lecture today. Now, our Associate Director of Science, Randall Smith, is going to be introducing today's lecturer.
I sympathize with Lisa's concerns. I just always knew him as Aad, which was much easier to say. But I had many times shared coffee with him at the SSP coffees when I was here as a postdoc. But my job here today is to introduce Dr. Gary Zank, who received his PhD in applied mathematics from the University of Natal in South Africa in 1987. He then did a postdoc at Max Planck, two of the Max Planck Institutes, then the University of Delaware, then moved straight into becoming a professor at the University of Delaware, well done. Was there until 2000 when he moved to UC Riverside, until 2008, and then to his current position at the University of Alabama, Huntsville in 2008. The list of his titles is quite impressive. It's Gary is an eminent scholar and distinguished professor at the University of Alabama, director of the Center for Space Plasma and Aeronomic Research, and chair of the Department of Space Science at the University of Alabama, Huntsville. He's been recognized throughout his career with the receipt of multiple honors and awards, including the Zeldovich Medal from COSPAR, the Russian Academy of Sciences. He's a fellow of the American Physical Society and received the NASA Silver Achievement Medal for his work with the Parker Solar Probe team. In 2017, he was named the University of Alabama Board of Trustees Trustee Professor, the first and only professor with this title. This was perhaps a recognition that in 2016, he was elected to be a member of the National Academy of Sciences, a rare honor, and the only person at the university to be a member of the body. Today, he'll be speaking to us on the heating of the solar corona and the accretion of the solar wind, insights, theory, and modeling emerging from the ESA Solar Orbiter and the NASA Parker Solar Probe missions. Many thanks.
So hopefully everyone can hear me. So thank you for that very kind introduction. And a lot of South Africans, in fact, live in Australia. And I say van Ballegooijen, which is more of a South African way of pronouncing it. I always felt that the Dutch had a very English way of speaking Afrikaans to some extent. But in any event, so I'd like to welcome the family. It's a great honor to meet you. And Aad has been a sort of fixture in the solar physics community for a very, very long time, and I think was a great not only mentor, but just an example to many of us doing science. You'd heard mention of his empathy and his kindness towards students and postdocs and so forth, and I've seen that happen multiple times, and so Aad was somebody I admired greatly. So I thought I'd talk a little bit about one of the topics that Aad spent a great deal of time thinking about and in fact mentored for quite a number of years one of our students from the University of Delaware, Stephen Cranmer. Stephen did his PhD in a quite different subject, but I guess he hung around both Bill Matthews and myself for long enough to actually learn some turbulence. And so he spent a great deal of his time either teaching Aad some of those turbulence ideas that we had and learning from Aad a great deal about solar physics. And so I wanted to put a little bit of that together in today's presentation. So one of the sort of seminal and most, I think, exciting events in the past decade really has been the Parker Solar Probe and now the European Space Agency Solar Orbiter mission as well. And the combination of that and in principle DKIST, which came online not so very long ago, although I won't talk about that, has really rendered this time we're living in as something of a golden age for solar physics. And so I think it's probably appropriate as well that today's presentation is about that. So kind of in the spirit of Aad, the list of authors that you see over there is a multinational, multi-generational group. Some have been my students, some are currently my students, others are postdocs, some are in the Czech Republic, others hail from Turkey, Italy, and then of course we have Justin and Stuart Bale, who many of you will know very well. I thought I'd just begin by perhaps just showing a photo, apparently according to Sarah, just before fondue was about to be served at the ISI, at an ISI meeting. This was back in 2009. And there's some very, very young characters in there that seem to have undergone a little bit of a metamorphosis since. I won't point out or pick anybody out in particular. But I thought just on the right, I would just talk a little bit briefly about the work with which I'm most familiar that Aad did. And so the first is coronal loops, magnetic fields, heated by reconnection events. He spent a lot of time looking at this nano flare idea that had originally been initiated, I guess, by Gene Parker many years ago. This idea that you twist and braid magnetic field lines. and you then dissipate the energy that is produced by that twisting and braiding, provide some form of heating and energization into the plasma that may or may not drive the solar corona, or heat the solar corona, and drive the solar wind. But really it's the second one that I wanted to talk a little bit about, in part because of that connection with Stephen Cranmer, Aad's work on this, and some of the work that he utilized that I had done as a postdoc in part. And this is coronal heating driven by the dissipation of MHD waves. And so I apologize in advance if I use terminology and ideas that may not be completely familiar to everybody in the audience, but you're welcome to stop me and ask questions at any point. And so a lot of this work really was initiated and found quite full expression in a 2011 paper that Aad wrote, where he in fact introduced this idea of using reduced MHD into modeling the dissipation of fluctuations in the solar corona and in the chromosphere, and then asking whether that was sufficient to in fact heat both of these regions and hence drive the solar wind. And so the idea is that you basically have these magnetic field lines. The magnetic field lines are a bit like fairly stiff strings low down in the corona, and if you shake them up enough, they produce little kinks and fluctuations that then propagate upwards and produce these things that are called Alfvén waves. So when I say Alfvén waves, think of strings with fluctuating waves that propagate along those strings. There is a little complication associated with this that was sort of, I guess, in part work that had resulted from some of our earlier studies of turbulence, which is that if you have large-scale gradients in this kind of arena, what happens to those waves as they propagate along the magnetic field strings is that they can start to reflect, and you produce then counter-propagating fluctuations. And when you produce counter-propagating magnetic fluctuations, you can do interesting things with turbulence, as I'll describe. Effectively, you generate turbulence, and that turbulence can cascade to very small scales at which you start to then dissipate the energy in the form of heating the background plasma. And so that was one of the, I think, great areas of work that Aad was deeply involved with. So what Aad was really studying in this particular regard, very, very simple statement of the problem. It's been around for a very, very long time, basically since the start of the space age. And it's simple. The sun, the surface of the sun is only 6,500 degrees Kelvin, relatively cool, and certainly not enough to expand to cause the whole atmosphere of the sun to expand at a very high speed. The temperature that's needed, in fact, to account for the solar wind expanding at a supersonic speed is something on the order of 1 million or more degrees Kelvin. So you've got to go from 6,500 degrees Kelvin to 1 million degrees in order to produce that solar wind. How do you do it? We were fully aware, as I flew in yesterday, of course, I was at 30,000 feet, and it was very cold up there, and as I came down, the air warmed, and I had a balmy 80 degrees at ground level in Detroit. So quite the opposite happens in the solar corona, the atmosphere of the sun. So why do you heat the sun's atmosphere from 6,500 to this well over 1 million degrees? And so that was the question that Aad spent a lot of time thinking about. What heats the solar corona? So I would regard this as still one of the great unsolved problems in solar physics. And so you want to explain this. And of course, theories come in multiple different flavors. And for me, this is a pretty good theory. And in fact, at one point, I felt that many of the theories explaining the heating of the solar corona probably had some form or another of this. There's kind of this, well, this happens and that happens, and then, something magic, and you produce the solar wind. Okay. So this is more or less what I'm going to talk about, and this is where it gets a little more technical. So I'm going to look at the heating problem, and I'm going to talk about the magnetic carpet, which is something that Aad spent a lot of time thinking about. So, I knew I'd gone too far. So the magnetic carpet is an interesting, let's see if I, yeah, is just an interesting sort of component of this whole puzzle. So if you go down to the photosphere, and that's a very complicated, busy-looking plot at the top left, and what that shows is the surface of the sun, the photosphere, and what you see is this incredibly complicated magnetic field structure. And you see all those little loops that are coming up from the surface of the sun, and they have all different scale heights. So some can be very high, some can be much smaller. That network of magnetic field fluctuations is sometimes called the magnetic carpet as it emerges out. That's what you're trying to deal with and explain mathematically and try to convert that magnetic energy to something in terms of heat. And so you can get a rough idea of how much heating is needed. So again, for the people in the audience not particularly familiar, just above the photosphere is the chromosphere. The chromosphere looks relatively cold. If I take a look at this figure over here, you can see that the temperature, which is plotted on the left and the density is plotted on the right, you can see that the temperature doesn't seem to be particularly hot. That in part is because there's a lot of energy going into heating that, but that energy is also being rapidly cooled through radiative processes. And so you need to maintain that chromospheric temperature. Then you go through this incredibly sharp transition region, which is only a few hundred kilometers perhaps in thickness before you go onto that top, very much hotter region of the solar corona. And in order to heat the solar corona, you've got to put in, again, a great deal of energy. And so you can sort of make a rough estimate of how much energy is needed. And it's that number, 4 times 10 to the 6 ergs per square centimeter per second, that is required for chromospheric heating. And you need almost as much, about an order of magnitude in energy to heat the corona above about a solar radius. And so you can do some old kind of models that Withrow did, very famous models, where you look at a model that Parker had produced, which just said, I've got a lot of heat close to the sun, a very hot corona, which will then produce the solar wind as we understand it. That's that dashed line. If you take into account the radiative balance that's associated with the chromosphere and the heating that's needed, which is what Withrow did, you can kind of explain the solar wind going through the chromosphere and into the corona and into the supersonic solar wind, eventually reaching a speed of perhaps 400 or more kilometers per second. So I'd mentioned the magnetic carpet, and this is one of the things that Aad had looked at in some detail. There's the Cranmer part of what Aad was involved in, 2010 paper, where people began to look at the idea. In fact, Aad was the first, and I kind of made a joke to Ed DeLuca earlier that he seemed to be about 8 years ahead of where I was thinking at each stage. So in 2010, he'd begun to worry about this magnetic carpet. So what is the magnetic carpet? It's this basic magnetic field that rises up out of the photosphere. And for a while, it had, there was initially the idea that there was a 40-year cycle as this field would sort of rise up in these small-scale loops above the photosphere, and then and it's of mixed polarity, so there would be a lot of reconnection and so on, and partly this was what motivated Parker's idea of the nanoflare model. It was first thought that this cycled through on a 40-hour time scale, and then it went down to 14 hours, and now even some estimates suggest that it's even faster time scale of 1 to 2 hours. So you're replenishing this magnetic field on a very rapid time scale. And so these ephemeral regions, as they're called, appear to have little or no correspondence with sunspot cycle or latitudinal dependence. You see it everywhere over the sun's surface. The fields in these ephemeral regions can be quite large, on the order of 100 Gauss. You can estimate the pointing flux, so this is the energy that's carried in the magnetic field. It can be anything from 10 to the 6 to maybe 10 to the 7, or even 5 times 10 to the 5, depending on which estimates you want to play with. But there's a lot of energy in that pointing flux associated with this. And this was the point that the Cranmer and van Ballegooijen paper made in 2010. This is a possible mechanism for driving the heating the corona and driving the solar wind. There's some details about the height of these magnetic carpet loops. You can see they can be fairly large, but they're pretty much all over. And so in this 2010 Cranmer and van Ballegooijen paper, they were suggesting that maybe magnetic reconnection, analogous in a way to the nanoflare type of idea that Parker had advanced, it may be a possibility for driving the solar wind. So there are two different kinds of solar wind, which you're probably aware of. On the left, there's the sort of wind that comes out of large coronal holes, and that produces this very fast wind, typically, perhaps anything from 400 to 700 kilometers per second is the sort of speed that is produced typically from that. You also have a slow solar wind. The origin of the slow solar wind is also pretty hotly debated. One idea here, which is related to work that Len Fisk and his colleagues did, is you effectively heat up loops, and you suppose that those loops come together. They undergo a process called interchange reconnection, and that interchange reconnection in effect liberates that hot loop plasma, and that plasma then flows possibly at a greater height above the photosphere, and then forms the slow solar wind. You expect this kind of behavior to happen a lot in the equatorial regions of the sun. In both cases, you still need to heat plasma, and so it would be nice if you had one mechanism that basically heated both those processes, but you effectively changed, in some sense, the boundary conditions. Loops are closed, so you can have slightly different physics as a result of that, but open field regions may involve slightly different boundary conditions. But one would like to see the same kind of process under providing that kind of heating. So let's look a little bit at the nature of turbulence and just have a brief overview. So this was a nice paper that Stephen Cranmer had put together in 2015, where he basically said, we all agree on the following, and basically there's enough energy in the convective motions of the sun to heat the corona and the solar wind. That kind of convective movement, granulation, injects energy into a complex magnetic field. I showed you a sort of sketch cartoon of that. Very complicated, and the real situation is even more complicated. There's some magical process that basically takes that magnetic energy and converts it to heat. And then that gets transported through the chromosphere, and from the chromosphere through the transition region into the corona, and that heat is dissipated. How do you do that? You've got interesting things. Because it's a hot coronal plasma, you have the strong pressure divergence of the pressure tensor, and that is what is primarily the driver, at least for the sun. So you need to somehow heat that corona and provide that excess pressure. So in this 2010 paper, Art and Stephen had introduced sort of a dual concept. They basically said all the physical models that you can think of that drive the sun, that are associated with heating, fall into either this wave turbulence type of model, which is what I'll talk about in a few minutes, or a reconnection loop opening model. And so it was the reconnection loop opening model that the 2010 paper was addressing, which is basically we directly heat the plasma as a result of the interaction of magnetic carpet structures, which are of opposite polarity, and you produce all this reconnection that then heats the plasma. So that's a kind of easy one to sort of follow. What about the wave turbulence model? So this model actually grew out of a conversation. Ian Axford was actually visiting the University of Delaware where I was at the time, and he had given a series of talks about the model that he and my PhD supervisor, Jim McKenzie, had kind of put together a number of years, and that was, they called it the furnace model. And it was essentially a similar idea as this kind of reconnection, loop opening type of model. And Ian had been quite dismissive initially of the idea of Alfvén waves. They just propagate very fast, and he said, and there's no mechanism by which they dissipate. And Bill and I had been working at that point for a number of years on this idea of turbulence in the solar wind and how it is dissipated. And the essential idea is that you can have outwardly propagating fluctuations, but in propagating through a medium that has a gradient, you tend to produce reflected waves. And then when you have counter-propagating alphanic fluctuations, what happens is that those interact in a resonant way. And there's a relationship. Essentially, they interact in just the right way to produce what's called a zero-frequency mode. Basically, it's a mode that doesn't propagate. It looks like effectively a magnetic island. So it's just a little loop of magnetic structure. And that then is the thing that sort of prompts this turbulent interaction that then leads to a cascade of energy from very large to very small. So basically you sort of continue down this inertial range going from K to K to K in wave number space, mediated by these small scale fluctuations of a 2D kind. And so that idea was sort of well established, and we were able to show that both the evolution of turbulence from one astronomical unit all the way to close to the termination shock could be described by a pretty simple model that looked like what is called a WKB model. A WKB model is just a Alfvén wave propagation model without dissipation. It transpires that the sort of transport part of this turbulence description can be described by something that looks like WKB theory, but it also has a dissipation in a conventional turbulence manner. And so we spoke to Ian about this and said we didn't really agree with his ideas about Alfvén waves and the solar corona, and that was where we wrote this 1999 paper in which you've got fluctuations that propagate, initiated possibly at the base, launch waves outward. They propagate into this gradient, this inhomogeneous plasma, and they begin to reflect. And then as they reflect, you have counterpropagation, which then leads to this kind of turbulent interaction and then cascading down to these very small scales that then heat the plasma. And so then a lot of papers were sort of developed from there. So one of the earliest was this Cranmer, van Ballegooijen, and a number of other authors in 2007 that really took this idea and began to do some very detailed modeling of this process. And then there were more papers. Van Ballegooijen in 2011 was the one that I mentioned later, which took it to a quite new level. There was a 2011 paper that Stephen and Art had put together. And then this work, as I said, almost doing the cascading thing in terms of papers, except, yeah. So the nice thing about this is that it has a couple of important elements. First of all, you distribute the way in which you heat over extended distances. The nanoflare model just kind of like heated everything right at the base, and everything had to be super hot, and we saw that it wasn't. So how did you move from for example, the chromosphere through and higher up into the corona without dissipating all of that heat? You also expect that the cascade it's a quasi-perpendicular kind of cascade, and that's an interesting thing because it tends to heat plasma in perpendicular rather than parallel directions, and so it has that additional nice little feature to it. So that's sort of an introduction to these wave turbulence models. What about the loop opening model? As I said, here you tend to have these loops that come up. They move all around. They're of opposite polarity. So sometimes a field line that is oriented in one direction meets a field line that's oriented in the opposite direction. When they bump together, you have reconnection. And so that was the sort of nanoflare idea that goes back to 1972. And so that, to some extent, was the prevailing view on much of this. And to some extent, Art was using this kind of approach in discussing these loop opening reconnection models. The situation's more subtle, though, and you've got to worry a little bit about, again, how do you transfer this magnetic energy that you have so that it's distributed over a large range, spatial range of scales. And so it's a lot easier to generate turbulence that gets carried out. What transpires, and I'm not going to go through this little set of cartoons, I'll just show you some simulations, since people believe actually, I'm not sure. People believe cartoons before they believe simulations, but these look a little bit tricky. But you can use something called sort of component reconnection. And so when you produce when you have oppositely directed loops of a small scale, they will sometimes produce things that look like structures rather than waves. And part of the difficulty with waves is you've got to shake this very stiff piece of string very quickly in order to initiate a wave. And so the magnetic fields are very large and carry a lot of energy, but it's like, you want to shake not a piece of string, but a piece of steel rod. And so whether you can produce a wave along a steel rod is a little more difficult than producing a wave along on a piece of string. So what I want you to look at here, this is kind of a three-dimensional box, and what it has is open field in the sort of z direction, and there's so we sort of push the field together in the xy plane, and it's periodic in that same plane. And so what that does is initiate reconnection. And what I want you to do is to look at the bottom of the box, which is at the bottom there, and look at the structures that form. And it goes kind of a little bit fast. But look at this. What does that look like? It looks more like smoke rings and things of that nature. I can play that again, or I can go to the next one, which has just cuts through it. And so there you can see that it looks a little bit like a comb. So you see this magnetic field that's going out. And what you do is you look at this again, and what you see is you see all these kind of curious smoke ring structure-like, the presence of these structure-like magnetic fields. And so it begins to look not so much like waves. You don't see very many. I mean, here you can see something moving around like a wave, but not very much. But what you tend to see is all of this kind of smoke-like structure. And so you can look at that, you can analyze it as is done at the top left there, and you can pick out that, in fact, you see quasi-2D structures of the kind over here, and they tend to fill up this K perp to the minus 5/3, which for people in the turbulence community sort of looks like a Kolmogorov description of turbulence in either water or any other gas that you might like. But it seems to be a signature of these kind of self-similar processes of cascading from large scales to small scales. And so it appears that there's a great deal of energy induced in this kind of structure. Oops, I don't need to go through that again. So let me, okay. Okay. So that may be one argument for why you see 2D structures in turbulence. So here's another argument, and this, in fact, is something that Aad had thought about as well. And I've sort of put it into more of a cartoon form here and done some sort of rough estimates, but it's related closely, as I said, to the work that Aad had thought about in terms of the magnetic carpet. So going back to that little figure which showed the density and the temperature plot and the sort of behavior of the chromosphere and the corona. So imagine, for whatever reason, you can, in fact, produce a lot of alphanic fluctuations at the photosphere, and these propagate out into the propagate up into the atmosphere of the sun. So the first thing they're going to do is run into the transition region, and that transition region has this very, very sharp gradient as is illustrated over there. And I mentioned before that smaller gradients tend to produce reflection when you look at these turbulence transport models. Well, this idea actually goes back to work that Alfvén and Folthammer had written up in 1963, and a number of other people had played around with this idea, but not thought about it in quite this way. And that is, if you produce a lot of Alfvén waves propagating up, how many will actually be transmitted from the chromosphere into the corona? And you can make a simple estimate. It's not terribly hard to do, but it turns out that if the flux is Fa, a particular number, then the transmitted flux is on the order of 10 to the minus 4 or so smaller. So you produce a ton of Alfvén waves, and almost nothing gets through the transition region because they're all reflected backwards. So that was kind of interesting. You can use this estimate that I'd mentioned for, related to the pointing flux from the magnetic carpet, for example. But what is interesting about this, and what I pointed out a few years later, is that what do you do when you produce counter-propagating waves? You produce, in effect, this resonance condition between these outward and inward propagating fluctuations that produces what? Basically, quasi-2D zero-frequency modes. Why are those zero-frequency modes interesting? Well, they kind of just sit there. They don't propagate. You don't lose them. And they get slowly advected in the background flow. And as they're being advected, they're undergoing all these nonlinear interactions with one another. And as they undergo the nonlinear interactions, cascading from large scales down to small scales. And so you produce this distributed heating associated with the dissipation of those fluctuations. And it starts low in the chromosphere because of this counterpropagation, and is then advected, has no problem going through the transition region. It just advected through the transition region, and you then end up basically heating the chromosphere, and you heat the corona. And so it's a mechanism basically, again, saying most of the stuff that gets through is going to be more structures than alphanic. And so for me, it's not been a great surprise. I mean, we get papers written in Nature because you've seen an alphane wave in the solar corona. And in fact, one of your esteemed colleagues, Jonathan Certain, in fact, had a very nice Nature paper using sounding rockets identifying, and I think maybe, Ed, you were on that paper, where you saw what looked like alphanic fluctuations. But my point is that you write a paper because you see an alphane fluctuation. It's not because they're so common that you just can't help but see anything but alphanic fluctuations. So you only have to convert a small percentage of this to heat the corona, it turns out. So here's that little cartoon. This will sort of go. But what are the sort of, this kind of gives you an illustration of how magnetic flux ropes or plasmoids or magnetic islands interact with one another. And you can see that it becomes a highly turbulent, complex mess. And you can see that you generate small magnetic islands, large magnetic islands. There's an instability associated with this process, and you produce a lot of energy, and you end up with a great deal of that dissipation going on. And this is just driven as you just push these magnetic field lines that are oppositely oriented together. Okay. So where I departed from art is in what is it that primarily, what represents the turbulence at least in the atmosphere. And so it goes back more to Art's reconnection and loop opening models than it does to the alphanic fluctuations. And so you can start exploring this idea, looking at the plasma in its different environments, and you can put together, and I have backup slides if you want to look at that, but I've thought a page of equations would probably not go down especially well. I can speak and happily show you afterwards, but I can speak in a hand-waving kind of way. You can look at the generation of turbulence, and you can say to yourself, oh, what happens now if I in fact consider quasi-2D turbulence as being the primary driver? And so when you do that, you can sort of, and this went back to a very simple 2018 paper, and that's why I said I'm 8 years behind Art on all of this, because Art's 2010 paper was sort of asking about the magnetic carpet and whether or not this was something that could be used. This is a 2018 paper that said, yes, it can, perhaps from a slightly different perspective, because what you want to do is use the turbulence that's generated by the magnetic carpet in those simulations that I showed. And if you do that, can it account for the heating? And you can put together a very simple toy model. And toy models are hugely useful in actually all aspects of physics, because it's that tends to convince people that it's maybe a more plausible explanation than having just yet another very large simulation run ab initio. Better yet, do the toy model and then run the simulation and hope that they agree. But the important point out of all of this is you can look at the quasi-2D and the slab that's the alphanic-like turbulence, and ask whether the dissipation, in fact, does heat the solar corona. And you do find that, in fact, it gets up to close to 2 times 10 to the 6 K, basically 2 million degrees and quite rapidly. And so one of the interesting predictions with this is that it heats rapidly. So within 2 to 3 solar radii, you expect that temperature to be that hot and the flow to already be accelerating, which is somewhat different from the wave-driven kind of turbulence model, because that takes a much, much longer scale to generate the backward propagating fluctuations. So you can go through all the modeling, and I'm not going to bore you with that, but what you can use is Parker Solar Probe and Solar Orbiter in 2 very nice ways. And so every now and again, Parker and Solar Orbiter, as shown in that top panel, are radially aligned, and in the sense that Parker measures a plasma parcel at some close-in orbit at time t0, and then that plasma parcel is advected through the solar wind to eventually intersect with the solar orbiter. And so you can find a number of those radially aligned efforts. And so Daniel Telloni, Laxman Adhikari, we've been looking at those radial alignments, and the idea is, can we determine what the turbulence and heating looks like at location 1 and location 2 measured by solar orbiter, and is it consistent with the models that we've produced? The other one, which is even more interesting, is these kinds of conjunctions between Solar Orbiter and Parker Solar Probe. So Parker Solar Probe is much closer in. It's the little red dot over there. And so at T0, for example, Parker Solar Probe is about to enter the field of view associated with the METIS instrument on Solar Orbiter. And what that instrument can measure, because it's basically a Lyman alpha instrument, it allows you to sort of measure and probe the velocity and density profile very close to the sun. And so it looks at regions that Parker Solar Probe will never reach. And so Parker Solar Probe can measure, in a sense, something that's further out radially, and METIS can make remote observations that are closer in of that same field. And so you can do, in that sense, the same kind of modeling close to the sun and ask how does that compare with what's observed at the Parker Solar Probe. So here's a figure where the sort of red diamonds illustrate what METIS observes, translated now to the radial velocity on the left bottom and to the density on the right bottom. And then the blue and the solid dots over here, triangles, correspond to Parker Solar Probe observations measured in situ, looking at that same field of view, looking at the same patch of plasma that was observed remotely by METIS. And you can also measure things like you can measure with Parker Solar Probe the temperature, for example, on the right, and you can also measure the energy and turbulent fluctuations. And what you find is that the flow very rapidly accelerates, becomes supersonic within 2 to 3 solar radii, and the density falls off in principle as this r to the minus 2 usual thing, and you can account for the Parker Solar Probe observations. So these are fairly complex models, but they do a surprisingly good job of correlating the kinds of observations that you can make close into the sun with Solar Orbiter METIS observations, and much further out with in situ Parker observations. So we seem to have, although I haven't shared the details, a fairly decent understanding of what we think may be happening. So here's where it gets really quite technical, and I apologize. So what you'd like to do is to say, okay, well, we've talked about structures, these magnetic islands, flux ropes, plasmoids. We've talked about alphanic fluctuations. We would dearly like to see in situ these kinds of structures to, in fact, account for whether or not our theoretical models are appropriate, or whether we're doing the Kelvin and Hobbes kind of example that we started out with. And so, for example, at 1AU, it turns out you can look at very fine-scale structures using a spacecraft MMS, and it has it's a sort of four spacecraft structures, and so it allows you to do sort of multi-point measurements, and you can construct things called omega k frequency wave number diagrams, basically dispersion relations from the observations. And so what's shown in those top two panels is in the solar wind, some work that Ling Zhao did, very, very nice work, where she found that there are the fluctuations in green, and she was able to plot them in terms of this frequency wave number space using the various telescope methods that have been developed for this multi-point measurement. And the interesting thing, the dashed line with the long red arrow pointing to it corresponds to fluctuations that lie on the flow velocity part of that. So those are not those are advected fluctuations and not propagating fluctuations. And the short arrow pointing to the dashed line shows the where Alfvén fluctuations should lie. And you can see that there are neither forward nor backward propagating Alfvénic fluctuations exhibited there. So this is an example of identifying structures. Another way you can identify structures is to use what's called a Grad-Shrafnov technique. Basically, you make spacecraft measurements and you solve the Grad-Shrafnov equation to then determine what that structure. And what you see are these kinds of quasi two-dimensional magnetic islands or flux ropes. And in one case, you can even see that there appear to be interesting interactions between those flux ropes. So these are present all over. There's another way of looking at this, which is, I think I'll just skip through this. It's using spectrograms, and you can find magnetic island structures in various places using those spectrograms. That's also a useful technique. And this is, in fact, Parker Solar Probe measurements that identified these particular flux ropes at I think, the third orbit and maybe even the first orbit as well. And so these are seen in the vicinity of the heliospheric current sheet. There's another, again, somewhat technical kind of curiosity, which is that when you look at the spectral features of these fluctuations in the using Parker Solar Probe data close into the sun, what you frequently find is that you see only outwardly propagating Alfvén waves, and yet these outwardly propagating Alfvén waves, which should simply be waves, appear to have interacted non-linearly, because what you tend to see is spectra that have a k to the minus 5/3 or an f to the minus 5/3 spectrum. Why should you see a turbulent spectrum for what would appear to be just outwardly propagating, non-interacting waves? And again, there is a theoretical model, but it requires the existence of these quasi two-dimensional structures. I'm going to skip this one. I'm sure nobody's that interested in why you can see particular forms of spectra. And so this became particularly noticeable in the subalfvénic flow, and I just point out these two spectra at the top here. This was the first of those subalfvénic intervals, and what you see is there's highly unidirectional. Basically, all the energy in this is all the fluctuations are basically propagating outwards. There's all very, very little. You can see almost maybe 2 orders of magnitude propagating inward, almost nothing inward. Yet you tend to see these spectra. So it's highly what's called imbalanced turbulence. The so-called Alsasser Z+ modes are dominant, so there are very few counter-propagating modes. So again, this raises a concern about the wave turbulence model. But you can explain that based on these hypothetical zero-frequency modes, but you can't see it. So the last little bit that I sort of wanted to go through then is there a way, in fact, of identifying these? And so this is one of the things that I've been sort of working on over the last really year and a half, is to try to identify these non-propagating modes in a parcel of plasma. I'll skip that. And so essentially what you can show is that there's a way of, in fact, decomposing a set of fluctuations that are not too crazy. You don't see shocks. You try not to cross current sheets. And effectively, you want to just decompose that 30-minute interval, for example, of fluctuations into the constituent modes emitted by magnetohydrodynamics. So you've got to look in the right scale. And there's my medical disclaimer, which is always written in small print, basically to say that in my case, that the linear mode decomposition analysis is not a model or a theory. It is simply a way of treating data and trying to identify what kind of fluctuations are present in that data. And so this is the sort of almost last slide that I wanted to show. So you can just look, for example, at magnetic fluctuations in the subalfanic interval. You can look in terms of F, but what's nice about this is you can convert that to wave number space because it's essentially small amplitude fluctuations that have a dispersion relation. And what you tend to find is that, in fact, there's a dominance of 2D fluctuations present in this flow. There's these primarily outwardly propagating alphanic fluctuations, and then you have a much, much smaller component of inwardly propagating alphanic fluctuations, possibly reflected. And so this is the wave turbulence kind of model, and this is this additional augmentation where you include those zero frequency structures. What's interesting about that is that these outwardly propagating alphanic fluctuations behave like alphane waves. They're basically propagating more or less along the magnetic field, and they're just regular fluctuating waves. These inwardly propagating ones turn out to be things called alphane vortices, not entirely, but effectively an alphane wave which has a very high angle, and so it's basically just rotating, and so it has a VA, but the KZ component is almost, or K parallel component is almost zero. And so these are alphane vortices, and this, to my knowledge, is one of the first really identifications of those kinds of structures in the solar wind. And then for those who like looking at the solar corona using radio observations, you can also look at and use this approach to look at at density fluctuations. And it turns out that these density fluctuations, again, this is probably more for a few people in the audience, those density fluctuations are essentially a mixture, more or less equal, of what are called ionacoustic modes. These would be slow magnetosonic modes, but because you're in a large plasma beta, they're basically ionacoustic. So ionacoustic modes and entropy modes. And so you can look at the anisotropy associated with that, and it appears that the scattering of radio waves, at least in the ion inertial regime, is more or less consistent with what has been inferred just from radio wave observations remotely. And Ed Contar has been, there's a T in there, and Ed Contar has done a lot of that work. So you get a great deal out of this, and so you can extract all of these kinds of different modes observed more or less in situ, and it appears to be consistent with our understanding, at least of turbulence at 1 astronomical unit. So the conclusions then, this is more or less suggests that Art was, I think, probably correct in suggesting that the magnetic carpet may very well be the primary driver of turbulence in one form or another, that heats both the chromosphere and the corona, and there's enough energy in there to power both. I've argued in distinction that kind of turbulence is primarily non-propagating, small-scale flux rope kinds of structures for possibly two reasons. One is that maybe what's naturally generated. If it's alphanic fluctuations that are more naturally generated, there's going to be this very strong reflection, and that reflection is very likely then to lead, again, to these kinds of structures. And so when you do that, you can more or less account for the observed heating and acceleration of the solar wind. You can go in and look at the various in situ observations made by both Parker and further out by Solar Orbiter, and you can identify, in fact, that these quasi-2D structures are a significant part of the turbulence. And so I wish Art were here to see that last statement. I think there is an emerging theoretical framework, which is rather better than the Kelvin and Hobbes version, with which to answer that enduring question of how the solar wind is heated. And much of it, as I said, goes back to Art's contributions in this field, starting many many, many years ago with some of the most seminal papers on the subject, 2010, 2011, and 12 I mentioned, and the subsequent papers as well. So we're, I think, somewhat in a golden age for solar and heliospheric physics. We may be now close to answering this 50-year-old question of how the solar coronal heating, the chromosphere as well, produces the supersonic solar wind. And I would say that Aad's many seminal insights into this problem have largely contributed to that work. So I'll stop here.
Thank you very much for that fascinating talk. I imagine we have a number of questions. We have time for at least a few. We'll take one here.
So I want to talk about the chromosphere. So ever since the 80s, so the days of Skylab and the Val model, which was produced here, so we've had a pretty clear observational or kind of semi-empirical understanding that there is a lot of stratification in the chromosphere. And this seems to be an observational insight that I think gets ignored in a lot of these heating models. Yeah. So the plasma environment is changing quite dramatically. Yes, you have a temperature minimum at around 4,000 to 3,500 Kelvin, depending on whether you believe some carbon monoxide measurements or not. So, and then suddenly you get a radical change in temperature where you're actually ionizing most of the hydrogen. Right. Those are two very different plasmas, one that's partially ionized, dominated by neutrals, and one that is actually becoming more fully ionized. So within your ideas of how we actually heat the chromosphere, how do you account for the fact that we see that temperature change in a very localized area? And how do you account for the very dramatic changes we see in the plasma environment in the chromosphere?
So that in part is there were two reasons why I sort of was migrating away from the whole wave turbulence idea, and that was one of them. The other aspect is I have problems getting waves back in. There's the Alfvén critical surface that's always been a problem for Alfvénic fluctuations. But the chromosphere, I feel, has been largely neglected by at least theoreticians like me and others because of its complexity. The problem always was that you can't dissipate Alfvén waves, it seems, in a rapid enough way. The production instead of advected structures, as long as they can nonlinearly cascade, means that you do a lot of the work very close to the surface of the sun. And so all of that heating is happening in a very localized location. So it's sort of a chicken and egg problem. You know, suppose I generate a lot of turbulence for one reason or another close to the surface of the sun using, you know, the sort of reconnection associated magnetic carpet mixed polarity idea. Well, that starts to heat the plasma, and the plasma slowly starts to move upward and outward. But and that rate at which you're slowly starting to move outward is probably more slow, and again, this is where really detailed models are needed, but it's probably more slow than the advection timescale. So the cascade timescale is probably faster than the advection timescale close to the corona, close to the photosphere. And so you're heating it a lot because the flow is not hot yet. And as you start heating it, the flow heats up, it starts to expand. You start moving the stuff out more rapidly. You're still moving the flow is still fairly slow, but you're still doing a lot of the heating, and it just slowly moves up. Eventually you reach the transition regime or layer. There's no problem about reflection or anything else that I was pointing out with Alfvén waves. The stuff, these structures are just advected through, and they continue to be advected through. So the beauty of structures is you get all the nonlinear interactions happening and semi-locally, while at the same time you're cascading through scales and carrying some of the sort of energy further and further away. So I've felt that this is more or less the key to trying to understand that incredibly complicated transition a chromospheric region with all the stratification. I mean, I was kind of, when you look at the plasma beta, for example, it goes from actually very large down close, right at the photosphere, and then very rapidly becomes very small. And so, how do you account for all of this? The only way you can do it is you've got to heat semi-locally, but still be able to distribute that heating energy at different levels. And so that's kind of why I went into this direction.
Another question? Josh.
Wonderful talk.
Thank you.
Did you have anything to say, do you have something to say on the spatial distribution in terms of X and Y as opposed to Z? What governs how the carpet is structured? And then I have one other question.
Okay,
if I can
so I
sneak
can
in
give
a
the very simple answer, and you probably argue differently with me, but
Okay.
I've pretty much taken at face value the kind of distributions that those various references provided, going back to Shriver and I'm just forgetting his name suddenly, where they suggested that carpet distribution was more or less evenly distributed. And why, again, I liked that, which I'd sort of hinted at in the cartoon, is to me, I don't want particularly a different method of heating a coronal loop, at least in terms of the physical origin of the fluctuations, than I want in say, an open region. The difference in the coronal loop, is simply I've got the stuff at both ends of the loop generating fluctuations. And so that boundary condition is really what changes loop plasma from, say, the boundary condition that I have in an open region, which is just I have one end open and stuff is escaping. So I'm sort of assuming uniformity in some sense.
If I can ask one brief question, is there any understanding of how this structure can eventually and rarely, but still powerfully, produce CMEs? Then it's something very organized, and how do you get there?
So I tend not to think of the magnetic carpet as being particularly important for that. Maybe I'm wrong, but I tend to see the larger structures where you may have various forms of flare initiation producing that. So I'm not suggesting anything different. Actually, I'm following the conventional wisdom as far as the generation of CMEs and so forth. I will point out that the question of where switchbacks originate, and some of the work that Stuart Bale did in a sort of 2-year-old now, I think, Nature paper, suggesting that you can track down the origin of switchbacks to very low, I'm not sure whether it was a corona or very low in the chromosphere, but I would suggest in the corona, but he seemed to suggest some sort of interchange reconnection was or could be inferred from those observations, which would kind of square with the way I tend to think of the origin of switchbacks, but not everybody agrees on that.
Okay, one last quick question, I think.
All right, great talk, Gary.
Thank you, Michael.
I have a quick question about how you supply the energy for the 2D structures, because you have the 2D structures generated at the surface, they advect out, but we know in the solar wind we have active turbulence. Mm-hmm. So if they just dissipated, we would be losing that.
Oh, no, that's right. I mean, I won't remind you about papers you should have read while you're doing your PhD, but much of the work that we've done, and we made this point already in I think the 1996 paper, is that there's local generation of turbulence, whether it's due to things like stream shear, which I think is particularly important. Shock waves too tend to generate that. So there's a multiplicity of processes that generate turbulence in situ. And in fact, if you want to account for the observed behavior of the turbulent fluctuations now pretty much from, I think Laxman's last calculation started at, I don't know what, something like 0.3 or 0.2 AU, all the way out to something, basically to the termination shock at 85 astronomical units. You can account for the observed sort of radial evolution of turbulence and the corresponding heating in the solar wind, which is non-adiabatic. And the only way you account for that is you have to have in situ turbulence, which doesn't have to be at crazy levels. It sort of falls off as 1/r², as you might anticipate, and that can account for it. So there's no doubt. And so those open loops, for example, we've open field land regions. We've looked also at the possibility where you may in fact see KH, Kelvin-Helmholtz type instabilities generated along the edges of open coronal holes. And that may well, Daniel Telloni has suggested that we've observed that. It's possible. It's a complicated kind of an inference to make from observations, but we've sort of put together models as well that would incorporate that. So.
Okay, let's thank our speaker again. And I believe he has to leave for the airport very shortly, so if you wish to follow up any questions, please do so now. Thanks again to the family for coming, and I hope you enjoyed our first inaugural lecture.